What if you could witness the entire story of existence, from the first spark of creation to the final flicker of the last star, all compressed into a single hour? Buckle up, because we're about to embark on the most epic journey imaginable, traveling through 13.8 billion years of cosmic history and trillions of years into a future so distant it defies comprehension. This is the complete timeline of the universe, and your perspective on reality will never be the same. Our story begins in absolute nothingness. No space, no time, no matter, no energy. Nothing. Then, in an instant so brief it makes a nanosecond seem like an eternity, everything explodes into existence. This is the Big Bang, occurring 13.8 billion years ago, and it's not an explosion in space, but rather an explosion of space itself. In the first trillionth of a trillionth of a trillionth of a second, the universe undergoes cosmic inflation, expanding faster than the speed of light, growing from smaller than an atom to the size of a grapefruit. This might sound impossible, but space itself isn't bound by speed limits. Only the things traveling through it are. During these first moments, the universe is unimaginably hot, around 10 trillion degrees Celsius, far too hot for atoms to form. Instead, we have a seething soup of fundamental particles, quarks and gluons, smashing together in a cosmic plasma so dense that light itself cannot escape. The universe is completely opaque, a blinding fog of pure energy. Then, in just the first second, the universe cools enough for quarks to combine into protons and neutrons, the building blocks of atomic nuclei. This is called the quark epoch, and it's when matter as we understand it begins to take shape. For the next 3 minutes, nuclear fusion occurs throughout the entire universe, creating the first atomic nuclei, primarily hydrogen and helium, with trace amounts of lithium. This is Big Bang nucleosynthesis, and it sets the elemental composition of the cosmos for hundreds of millions of years to come. Roughly 75% hydrogen, 25% helium, and everything else is barely a rounding error. But the universe is still too hot for electrons to bind to these nuclei. Free electrons scatter photons constantly, keeping the universe opaque like a thick fog. Then we reach 380,000 years after the Big Bang, a cosmic milestone known as recombination. The universe has finally cooled to about 3,000 degrees Celsius, cool enough for electrons to combine with nuclei and form the first complete atoms. For the first time ever, light can travel freely through space. The universe becomes transparent. This light, stretched and cooled by 13.8 billion years of cosmic expansion, is what we detect today as the cosmic microwave background radiation, a baby picture of the universe that astronomers study to understand our cosmic origins. If you could see this moment, the entire sky would glow with a dim reddish light, the afterglow of creation itself. Now we enter what cosmologists call the Dark Ages, lasting from about 380,000 years to around 150 million years after the Big Bang. Despite the dramatic name, this is a crucial period. The universe is filled with neutral hydrogen gas, dark matter, and radiation, but there are no stars yet, no galaxies, no light sources besides the fading cosmic background. Gravity is quietly at work, pulling gas into denser and denser clumps where dark matter has created invisible scaffolding. These dense regions will become the seeds of the first stars. Around 150 to 200 million years after the Big Bang, something magical happens. The first stars ignite. These aren't stars like our sun. They're massive monsters, perhaps 100 to 1,000 times the mass of our sun, burning brilliantly blue and living fast, violent lives lasting only a few million years. These population 3 stars, as astronomers call them, are made purely of hydrogen and helium, since no other elements exist yet. Their incredible nuclear furnaces forge the first heavy elements, carbon, oxygen, silicon, iron, creating the cosmic periodic table. When these giant stars explode as supernovae, they scatter these newly formed elements into space, enriching the universe and making future generations of stars and eventually planets and life possible. This era, called the Cosmic Dawn, marks the end of the Dark Ages. The universe is now dotted with blazing stars, their intense ultraviolet radiation beginning to reionize the hydrogen gas that fills space, splitting neutral atoms back into charged particles. This epoch of reionization continues for several hundred million years, fundamentally changing the character of the cosmos and making it more transparent to different wavelengths of light. By 400 to 500 million years after the Big Bang, the first true galaxies begin to form. These early galaxies are small, irregular, chaotic collections of young stars, nothing like the majestic spiral galaxies we see today. They're more like building blocks, proto-galaxies that will merge and collide over billions of years to create larger structures. Dark matter plays an invisible but crucial role. Its gravitational pull creating the framework around which normal matter can accumulate. Around 1 billion years after the Big Bang, the universe is becoming increasingly structured. Galaxies are growing larger through mergers, and the first supermassive black holes appear at their centers, some already containing millions or even billions of solar masses. How these black holes grew so massive so quickly remains one of astronomy's greatest mysteries. These cosmic monsters power quasars, the brightest objects in the universe, visible across billions of light years, shining with the energy of trillions of stars as matter spirals into the black hole's gravitational maw. At about 3 to 4 billion years after the Big Bang, star formation in the universe reaches its peak. This is cosmic high noon, the most productive era of star creation in cosmic history. Galaxies are colliding and merging constantly, triggering massive bursts of star formation. The universe is younger, denser, and far more dynamic than it is today. Heavy elements are becoming more common, incorporated into new generations of stars, and beginning to form the first rocky planets. Now we reach 9.2 billion years after the Big Bang, about 4.6 billion years ago in human reckoning, and we arrive at a specific location in an ordinary spiral galaxy we call the Milky Way. In an unremarkable region of one of the galaxy's spiral arms, a cloud of gas and dust begins to collapse under its own gravity. This is the birth of our solar system. At the center, the sun ignites, while the surrounding disk of material gradually coalesces into planets, moons, asteroids, and comets. Earth forms within about 100 million years, initially as a hellish ball of molten rock, constantly bombarded by asteroids and comets in a process called the Late Heavy Bombardment. Around 4.5 billion years ago, a Mars-sized object crashes into the young Earth, and the debris from this catastrophic collision coalesces to form the Moon. This impact tilts Earth's axis, giving us seasons, and the Moon's gravitational influence stabilizes Earth's rotation, creating conditions favorable for life. By 3.8 billion years ago, Earth has cooled enough for liquid water to exist on its surface, creating the first oceans. The exact timing is debated, but somewhere between 3.5 and 4 billion years ago, something extraordinary happens. Chemistry becomes biology. The first self-replicating molecules appear, primitive cells emerge, and life begins. These earliest organisms are simple single-celled bacteria and archaea, but they're revolutionary, the ancestors of every living thing that will ever exist on Earth. For the next 2 billion years, life remains exclusively single-celled and microscopic. But these microorganisms are busy transforming the planet. Around 2.4 billion years ago, cyanobacteria evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into energy, releasing oxygen as waste. This triggers the Great Oxidation Event, fundamentally changing Earth's atmosphere from oxygen-poor to oxygen-rich, creating the sky we know today and paving the way for more complex life forms. Around 600 to 800 million years ago, the first multicellular organisms appear, simple but revolutionary. Then, 541 million years ago, life explodes in diversity during the Cambrian explosion, when most major animal groups appear in the fossil record within a geologically brief period. The oceans fill with a bewildering array of strange and wonderful creatures, from trilobites to anomalocaris, establishing body plans that will persist for hundreds of millions of years. Life moves onto land around 500 million years ago, first with plants, then with arthropods, and eventually with vertebrates. The continents are constantly shifting due to plate tectonics, sometimes clustering together into supercontinents like Pangaea, sometimes fragmenting apart. Mass extinctions periodically wipe out large percentages of species, including the devastating Permian extinction 252 million years ago that killed about 96% of marine species, and the famous Cretaceous-Paleogene extinction 66 million years ago that ended the reign of the dinosaurs when a massive asteroid struck the Yucatan Peninsula. This asteroid impact creates an opportunity for mammals, previously small and mostly nocturnal, to diversify and grow larger. Primates evolve and eventually give rise to hominids. Around 6 to 7 million years ago, the lineage leading to humans splits from the lineage leading to chimpanzees and bonobos. The genus Homo appears about 2.8 million years ago, and anatomically modern humans, Homo sapiens, evolve in Africa around 300,000 years ago. For most of human existence, we live as hunter-gatherers, developing increasingly sophisticated tools, language, art, and culture. Around 12,000 years ago, the agricultural revolution begins, and humans start domesticating plants and animals, settling in permanent communities and developing civilizations. Writing is invented about 5,000 years ago in Mesopotamia, marking the transition from prehistory to recorded history. Human civilization advances through various stages, from ancient empires to classical civilizations to medieval periods to the Renaissance and the scientific revolution. Technology accelerates exponentially. In the late 18th and 19th centuries, the Industrial Revolution transforms human society. The 20th century brings automobiles, airplanes, nuclear energy, computers, and space exploration. On July 20, 1969, humans walk on the moon for the first time, a remarkable achievement just 66 years after the first powered flight. The 21st century sees the rise of the internet, smartphones, artificial intelligence, and renewed efforts to explore space with missions to Mars and beyond. We stand now in 2026, approximately 13.8 billion years after the Big Bang, living on a 4.5 billion-year-old planet, members of a species that evolved just 300,000 years ago, but has already begun reaching for the stars. But what about the future? We've covered the past, now let's journey forward into the unimaginably distant future. In the cosmic calendar, human civilization is but the blink of an eye. The universe has so much more story to tell. In the near future, within the next few thousand to million years, human destiny depends on our choices. Climate change, resource management, technological advancement, and potential expansion beyond Earth will determine whether humanity thrives, stagnates, or goes extinct. If we survive and expand into space, we might colonize the Moon, Mars, and eventually other star systems, becoming a multi-planetary or even galactic civilization. Around 1 million years from now, if humans still exist, we will likely be so genetically, technologically, or culturally different from current humans that we might be classified as a different species entirely. Stars in our night sky will have shifted noticeably from their current positions. Several nearby stars might have evolved off the main sequence, becoming red giants or white dwarfs. In 50 million years, Africa will likely collide with Europe, closing the Mediterranean Sea and creating a massive new mountain range. The continents will look significantly different from today. Many current species will be extinct, replaced by new forms evolved to fill ecological niches. 250 million years from now, Earth's continents may merge into a new supercontinent, sometimes called Pangaea Proxima or Amasia. The climate will be dramatically different, with a vast interior desert and limited coastlines. Life will adapt to these new conditions, potentially producing entirely new ecosystems and body plans we cannot imagine. Around 600 million to 1 billion years from now, Earth faces a crisis. The Sun, though still on the main sequence, has been gradually brightening throughout its life, about 10% per billion years. This increased solar radiation will trigger a runaway greenhouse effect on Earth. The oceans begin to evaporate, water vapor traps more heat, temperatures soar, and eventually Earth becomes uninhabitable for complex life. Microbial life in protected environments might persist longer, but Earth's days as a living world are numbered unless humanity or its descendants intervene. At 5 billion years from now, the Sun enters its red giant phase. Having exhausted the hydrogen in its core, it begins fusing hydrogen in a shell around the core, causing the outer layers to expand dramatically. The Sun grows to perhaps 100 to 200 times its current size, engulfing Mercury and Venus. Earth's fate is uncertain. It might be consumed, or it might survive in a wider orbit as the Sun loses mass, but any remaining atmosphere and oceans will long since have boiled away. Earth, if it survives, will be a scorched, lifeless cinder orbiting a bloated red star. After about 1 billion years as a red giant, the Sun will expel its outer layers in a spectacular planetary nebula, a glowing shell of gas expanding into space. Left behind is the Sun's core, now a white dwarf, an incredibly dense object about the size of Earth, but containing about half the Sun's original mass. This white dwarf will shine with residual heat, gradually cooling over trillions of years. But let's zoom out from our solar system and look at the broader universe. Over the next hundreds of billions of years, star formation continues throughout the universe, but at an ever-decreasing rate. The universe is expanding, driven by dark energy, and this expansion is accelerating. Galaxies or galaxy clusters not gravitationally bound to each other are moving apart faster and faster. In about 4 billion years, the Andromeda Galaxy and the Milky Way will collide and merge, a process taking billions of years and resulting in a large elliptical galaxy, sometimes called Milkomeda or Milkdromeda. Despite billions of stars being involved, actual stellar collisions will be rare because stars are so far apart relative to their sizes. However, the galaxy's structures will be completely disrupted and bursts of star formation will occur as gas clouds collide. Around 100 billion years from now, the universe enters an era called the degenerate era. Star formation has essentially ceased because most of the available gas has been incorporated into stars or locked away in stellar remnants. The universe is populated primarily by dead or dying stars, white dwarfs, neutron stars, and black holes, along with planets, asteroids, and other cold objects. The oldest red dwarf stars, the longest-lived stars possible, are still burning, but they're in their final stages. By 1 trillion years from now, even the longest-lived red dwarf stars have exhausted their fuel and faded. The universe is now truly dark. No new stars are forming, and all existing stars have died. The cosmos is filled with stellar remnants and black holes, occasionally illuminated briefly when objects collide or fall into black holes. The universe enters the black hole era. But the universe isn't static. Even in this dark era, things are happening. Stellar remnants slowly change orbits through gravitational interactions, occasionally being ejected from galaxies or spiraling into central supermassive black holes. Brown dwarfs, objects too small to sustain fusion, wander through the darkness. On truly incomprehensible timescales, around 10 to the power of 30 years from now, protons themselves may decay. This is highly theoretical and unproven, but if protons are not absolutely stable, then on these timescales, even white dwarfs and neutron stars will slowly evaporate as their constituent protons decay. The universe would become even more tenuous, filled with black holes, electrons, positrons, and photons. The black hole era dominates the universe until around 10 to the power of 100 years from now. During this unimaginably long period, black holes are the most massive objects in the universe. But even black holes aren't eternal. Through a quantum mechanical process called Hawking radiation, black holes slowly evaporate, emitting particles and losing mass. Smaller black holes evaporate faster. Stellar mass black holes take around 10 to the power of 67 years to evaporate. Supermassive black holes take far longer, around 10 to the power of 100 years. When the last black hole finally evaporates in a burst of radiation, the universe enters its final era, the dark era. Now the universe consists only of a thin soup of photons, electrons, positrons, neutrinos, and possibly other stable particles, all separated by truly cosmic distances due to the continued expansion of space. The temperature of the universe approaches absolute zero. No structures exist, no stars, no planets, no black holes, nothing capable of complex organization. The universe continues expanding forever, becoming ever more diffuse, ever colder, ever darker. This is heat death, the ultimate fate predicted by the second law of thermodynamics. Entropy has reached its maximum, all useful energy has been dissipated, and no processes capable of doing work remain. The universe doesn't end in a dramatic bang, but in an eternal whimper, an infinite expanse of near-nothingness, forever expanding, forever cooling, forever dark. This is the timeline of the universe, from the unimaginable violence and energy of the Big Bang to the cold, dark, infinite expanse of heat death. We live in what might be called the stelliferous era, the age of stars, a cosmically brief but incredibly special period when the universe is filled with light, energy, complexity, and life. On cosmic timescales, this era is vanishingly brief, perhaps just 100 trillion years out of a future that may extend for 10 to the power of 100 years or longer. Understanding this timeline changes your perspective. Every moment we have, every sunrise, every conversation, every discovery, occurs during this precious window when the universe is young, energetic, and capable of supporting complexity and consciousness. We are literally made of atoms forged in the hearts of dying stars, organized into patterns capable of contemplating the very universe that created us. We stand 13.8 billion years after the beginning, in a universe that will exist for trillions upon trillions of years more, living on a planet orbiting an ordinary star in an ordinary galaxy, Yet we've managed to piece together this epic story through observation, mathematics, and human ingenuity. The universe's timeline is not just a chronicle of physical processes, but a story of increasing complexity emerging from simple beginnings, of structure arising from chaos, of life and consciousness appearing in a cosmos that began as nothing but energy and fundamental particles. We are the universe becoming aware of itself, if only for a cosmically brief moment. As we look to the future, whether humanity survives for thousands, millions, or billions of years, we're still witnessing just the opening chapters of the universe's story. The stelliferous era, our era, is the universe's prime time, and we're fortunate enough to exist during it. What we do with this knowledge, how we choose to spend our brief time in this cosmic window of opportunity, that's the story we're writing right now. From the Big Bang to heat death, from infinite density to infinite expansion, from the first particles to the last black hole, this is the complete timeline of everything. And somewhere in the middle of that vast story, for just a moment, we exist, aware, curious, and capable of understanding it all. That might be the most remarkable part of the entire timeline.